somebody who's younger, and it's good to have fresh blood. At Twilight Moon, actually, she's going to be leading the next report. I have to apologize, my voice is still, I will have to stop because I'm still recovering from a little bit of whatever it was, laryngitis, tracheitis, whatever. And I thought that it was important to share with you some of the results from this summer, not only because the Arctic Report card is going to be launched at AGU. So technically there is a couple of things that are going to be revealed there, but we also, because Xavier Fetois, a long-time collaborator and a dear friend, we've been working also on a paper that is now published as a discussion paper in the cryosphere. So I feel comfortable sharing those results, and you will find a lot of those figures here in the paper. But the excuse here is also to have a conversation about what happened this past summer, how it's different from 2012, what are we learning, and also I wanted to show you some slides about the work at NASA GISS, about the ModelE especially, with most of the people who are sitting here also that we've been working in the past. Feel free to stop me. I like this to be more a conversation rather than a presentation, but of course you should know that, I mean, this is a very brief outline. The tools, I'm going to show you some application of passive microwave remote sensing. We use optical data. I have actually some fresh results that I got from Brian Loomis literally 12 hours ago about the updates on GrIS for in Greenland to September of this year, and the Arctic Report card has data through April. So there is a new data here, and then we're going to use MAR and ModelE and some in-situ data. We start with passive microwave. You know, we look at passive microwave for a while. What you see here is on the left, on your left, here it's the time series from April through October of the melt extent on the y-axis. That's basically the percentage of the ice sheet that is undergoing melting. With passive microwave, we can look at the melt extent. We don't know what the liquid water content is, even though there are some ways to extrapolate somehow how much water was produced. But as you see here, the blue dashed line, that's your mean for the 1981-2010 value. Then you have some standard deviation. But then you see that the red is the 2019, and the full blue line is 2012. Of course, you remember the huge peak in 2012 that reached mostly 90% or even more of the ice sheet. But you also see that similarly to 2012, the 2019 season started earlier, not as early and as strongly as in 2012, and you also had a very strong late melting. The map on the right is showing you the anomaly of the number of melting days from passive microwave. Again, the mean with respect to the baseline 1981-2010. You see that there are some areas where it's blue, which means below, but most of the areas, they are red, above the mean, and in some days in the northwest and northeast, which I found very interesting, because these areas, they've been accelerated, there's been a lot more melting, but they've been receiving a lot of less attention because the runoff is not as considered to be as important in these areas. But you will see there is a lot of extra melting, so to say, especially along the edges where the bare ice is exposed, where the dark zone of ice is also exposed. And again, you will see that there is a lot of melting up here, and we'll see also that the processes that are driving to the melting here and melting here are complementary, but can be slightly different even within the same season. And I think this is extremely important to understand for future projections. I was mentioning to you the GrIS. This is a figure that NOAA has put together for their release, but I stole it from them. So this is what they're going to use. And this is the updated trend for GrIS and GrIS follow-on. You see, I don't like the fact that they put a line. They should put the dots, but that's basically what they did. And I was only able to convince it to put a dashed line where there is the bridge between GrIS and GrIS follow-on. But bottom line, the message of this figure is that you have in the past summer, and this is updated through the beginning of September, you had, and this is expressed in trillions, but you had this much loss as in 2012, which is about 500 gigatons of mass loss within the summer. So you see the cycle, you see the ice sheet is gaining mass during the winter, and then it's losing it during the summer. You see that also during the winter and the spring before, there was really no gain, really little gain, and we'll see why. And of course, because of the snowfall.
Is there any issue with calibration?
The data was produced. Yeah, the data was produced by Brian Loomis. So they are doing the temporary intercalibration. So I don't know how they do it exactly. This is the stuff that Brian sent me yesterday. So there's no overlap between the two sensors. So,
right. So is there an absolute calibration?
I think they're using radar altimeters and other stuff to do the calibration between the two sensors. But yes, there is of course a potential issue of bias between the two sensors. And I don't know exactly.
How big that might be?
No.
If it moves up or down, then that
No, because this is what Brian has been able. They are developing now the mass column solution and the full one, so they will be able to do all the comparisons. This is based on their solution. They also sent me the JPL solution, that are very similar to these ones. But bottom line is 500 gigatons of mass loss within the summer, which is exactly the value that also we had in 2012. And most of it, a lot of it comes from runoff, as we will see. Going back to again to the time series using passive microwave, and to put things in the context, the red line, the blue line is showing you the percentage of the ice sheet undergoing melting at any time. So in the first slot, the first plot here, I was showing you this is for every day. You see that in 2012 you had this this day when there was a huge melt extent. But also, as you look at 2019, and if you take all the pixels that undergo 1 day of melting, then and you calculate what is the maximum melt extent, basically, you see that 2019 and 2012 are very similar, followed by, I think, this is 2003. Bottom line, these events are extremely important because, first of all, you don't see them happening before, and also the melting index is what we define to calculate somehow the strength of melting. So that melting index is the number of days times the area where melting is occurring, and it's giving a sort of measure of the energy, basically, that is required. So that it's slightly different from the extent, even though, of course, they are strongly correlated. But you see that in 2012, the melting index was higher, which implies or suggests the runoff or meltwater production was higher in 2012 than in 2019 based on passive microwave. So that's basically you can look at the trends, and all these plots and figures are in the crossfield discussion paper. You can look at them. Just to be sure, also one thing that we need to do with Xavier, because we are talking about 1 day of melt, how good is that? How reliable is the fact that you're taking 1 day of melting to use this measure. So what we did, this is the same image of melting days, but it's shrunk between 1 and 5 days, just to give you a better idea where melting is occurring. And if you plot the brightest temperatures, in these cases where melting occurs for 1 day only, or for 3 days, we did basically an analysis on a pixel-by-pixel basis to be sure that the melting that we were identifying was not due to calibration errors or sensors problems. But indeed, you see that there is a gain of about 50 Kelvin at summit, for example, in this case. And in this case also, there is a sustained brightness temperature increase that makes us think that then melting is actually real and it's not due to sensor problems. The other way also that we looked at, this is a temperature, air temperature time series from the PROMICE, one of the PROMICE stations, which are basically automatic weather stations deployed by the Danish Meteorological Institute colleagues to monitor the ice sheet. And you see this is the corresponding time series of brightness temperatures for the same pixel, for the pixel containing those station. You see that when the brightness temperature is exceeding the threshold calculated based on the brightness temperature above which we assume the melting is occurring, you also see that the air temperature was exceeding the melting. But you see also that happens in other cases. I think in this case, I'm not sure why there's no detector. I think it's because the air temperature, first of all, is different from the snow temperature. You can still have the temperature of the air is above zero, but you still have freezing conditions. Or in that case, probably the signal, the liquid water content within the snowpack was not strong enough to trigger the passive microwave wireless temperature increase. Lastly, because we care about processes, we also looked at what happened to the time series of the melt-albedo before and after this sporadic melting at high elevations. Again, we're looking at the dome, what was supposed to be called the dry snow zone. And this is the bar show the time series of ModelE's daily broadband albedo before and after melting occurs. And you can see that before that, maybe you have a little bit of accumulation because the albedo increases, which means that your grains are slightly getting smaller. But then as you have melting, the constructive metamorphy, the melting and freezing of the snow grains make them bigger, and you can really see that the albedo is dropping from about 87% to 77% within those days, just because as a consequence of the melting. And then it gains a little bit of, because the grains might break down, or because of the wind, or there could be new snowfall. But this is basically showing the consistency of one-day melting from the passive microwave and the physical consequences that you would expect to see on the ice. So we're pretty confident that whatever we were able to measure is on passive microwave is pretty there. It's not due to the sensor, but to me it's very interesting because one thing that I can show here, but we write in the paper, is that this actually event, it's true it did not happen in one day, but it did happen in 3 days. And it was the same, exactly the same weather event that triggered all the melting that you see here. And then lasted for about 2 days, and it moved literally to other areas of the ice sheet as the weather patterns were moving. And this involved up to 95% of the ice sheet. So it's true that from a climatological point of view, the two events of 2019 and 2012, they are very similar. Yes, in 2012 it was 1 day, then everything was melting. 2019 was 3 days, but it was the same climatological, the same event. So I think the two maxima can be put side by side if you look at the climatology, or if you start looking at the drivers, in this case the atmospheric drivers. And we use MAR, the ModelE atmospheric regional. We've been using MAR for a while, more than 10 years. It's a regional climate model, and it's forced at the boundaries, which are shown here, a little bit slightly larger, by analysis data. Then MAR has its own atmospheric model, and it's fully coupled with the surface model, which is based on CISBAC and Crocus, and it has a fully developed multi-layer snow model that resolves for energy and mass balance, and it's fully coupled with the atmosphere. So these are the results for, again, 2019. What you see here are, again, anomalies, and all these anomalies are referring to the same baseline period, 1981-2010. On the left, you have the melting, number of melting days, similar to what we derived from the passive microwave. In this case, in case you're wondering, the optimal configuration for passive microwave is sensitive to about 1% of living water content within the first meter of snow. And that what gives us the best matching with MAR, and this is something we published in 2007 exactly. So, and we found that works pretty well. You see the snowfall anomaly here, and as I was mentioning to you, you see that in the north there's a very little anomaly, but in the south there's a very strong below the average anomaly, and this is expressed in millimeter water equivalent. And you have albedo on the right side. This is still simulated by MAR. Just to let you know, MAR does not include impurities now, darkening of the ice sheet, but it does just have bare ice exposed once the snow is removed, and this is something that we're working on it. But you will see that the albedo values in MAR are slightly lower than the one that ModelE is fine. Yes, Dave?
Are the snowfall anomalies matched by an increase in natural rainfall?
No.
So it just didn't?
Yeah. You see the albedo again, all of the anomalies are negative, which means of course albedo was lower than the average. So of course there's a strong consistency between the reduction of snowfall and the reduction of albedo, because as you start melting the snow early, as it happened, if you have new snowfall, then you can mute the albedo effect. As you start melting the seasonal snow, of course, either you have a larger grain size that reduces albedo in the near infrared, or you can actually have also the exposure of the bare ice below. And if you don't have enough snowpack from the season or from the past winter, then you will expose your bare ice pretty sooner, and then you will have a much more energy absorbed within the same season. And we'll see what happens basically based on the model. So again, I was mentioning to you, this is the map of anomalies. The baseline periods are slightly different. In the case of ModelE is the 2000 to 2010, because the time series is different. On the right, and the same figure I was showing you before, but overall you see a strong consistency between the two products. As I was mentioning to you, MAR does not capture the entire darkening on the left, on the coast, because that is mostly strongly driven by the impurities presence, but also because modeling bare ice albedo is pretty difficult, and MAR now has a fixed albedo for bare ice. But there are steps that we're trying to undertake to model bare ice in a more physical way in MAR, so that you start accounting for the air bubbles and everything else, because those small differences can make a huge difference, especially when you have a strong incoming solar radiation and anticyclonic conditions like in 2019. But overall, there's a strong consistency, and one thing that I wanted to share with you also is this is the summer ModelE albedo anomaly. These are for the different months. You see that June was a pretty average month, but you still have a lot of strong negative anomalies along the east and west coast because of the bare ice exposure. July, the anomalies continue on the north and the northwest. In August, there is a strong anomaly, but also you see that a lot of anomalies are on the ice, on the interior of the ice sheet. This has really no effect on the meltwater production. This really has no effect on the runoff. You could say that if you take the integrated albedo, August will be the lowest, and we'll see that. But overall, a lot of these negative anomalies are due to the fact that you had a little bit of melting, as we saw in the beginning of the slides, and there decreases grain size, and you did not have a lot of new snow on top of that snow that could basically put the albedo back to original values. And so if you plot the time series of ModelE integrated over the entire ice sheet, for the dots is the entire summer, so you see that 2019 is not as low as 2012. But then if you start looking at August becomes low as 2012. But again, in 2012, you had very low albedo values because you had strong melting. You have the bare ice that was climbing up at high elevations. And so that was really impacting the mass balance of the ice sheet, where in this case in August, that is mostly a consequences of melting at high elevations, the lack of snowfall, and basically as a little effect on the mass balance of the ice sheet. So this is again to account for the processes that happen. And then if you put everything together by MAR, we started simulations in 1948, in this case using NCAR. And you basically will see that the yellow is the meltwater runoff in 2019. It's not as high as in 2012. So in 2019 there was less runoff in general than 2012. But then you start also seeing that in red, which is your snowfall, your anomaly is very, very low. It's within the mean. But then in 2012, again, you had also similar values. And then you look at the SMB, and then the SMB actually in 2019 is lower than 2012. So bottom line, the difference between the total mass loss from the surface simulated by by Mar between 2019 and 2012 is only about 11 or 12 gigatons. So that's really pretty much within the uncertainty in the area of Mar. And in a nutshell, the mass loss from surface due in 2019 was basically the same as in 2012. But the reason is different. The reason is that even though you have less meltwater production in 2019, because you have less snowfall, your mass balance is as low as in 2012, where you had basically more melting and slightly more snowfall.
Just for your
Yeah, go ahead.
So your August albedo anomaly, is it the case that you don't even need to melt the particles that you just got on the surface that would create?
Yeah. Bottom line, whenever you have a little bit of surface melting, once you refreeze it, because the albedo we're talking about is about 85–90%, it's very sensitive to the changes in grain size. And so in that case, a little bit of a melting creates this thin layer of water around the grains. When it freezes, it makes the grains bigger, or they're facetted and broken down. They start simply getting together because the water glued them together, and so they become larger scatterers. And even if they become slightly larger, the albedo drops because we're still in a very high sensitive area because the grains are still, the albedo is very high. But that has really no effect. I mean, you're changing about 5% absorption of the solar radiation, and there's no way that melting is going somewhere. It's only refreezing right there, and it's mostly staying there, or creating a slightly isolance like the one they found at Summit, which could be 1 or 2 millimeters, and then it get buried somewhere. Clara, did you have any?
Just one thing on the next figure. Sorry, the one after that. That transition is that runoff kind of around 2000?
Yeah.
Yeah, so do we understand why it's primarily negative?
Yeah, there's a switch, there's a very strong switch of the NAO, basically, the atmospheric conditions.
So this is the dynamically driven?
Yeah, this is basically what you see here a lot is really the signal of the NAO on the switching from the anticyclonic, from strong cyclonic to more anticyclonic conditions, probably more melting. And then we'll talk more a little bit.
Marco, when you have the ice lenses or the grains, does that impact how surface temperature is transmitted to the upper layers of the snow?
Yes, but I don't know exactly by how much now. That's something that Patrick would know because it was his early master thesis, something like a little bit long ago. But yes.
Huh?
But yes, there is, because that affects, of course, porosity, density, and but if we move forward, just looking at other maps, I was mentioning to you cloudiness. Look at this is the cloudiness expressed as a fraction of the pixel. You see that it's interesting that even though you have less clouds, some of the cloudiness in the top part of the Greenland ice sheet was actually positive. There were more clouds, and the lower part there were less clouds. So now the atmospheric scientists who are sitting here, not like me, but you basically start seeing that the presence of strong anticyclonic conditions sitting here, they promote high incoming solar radiation in the center, but the clockwise rotation is basically starting to push warm air and moist air over this region, and that's where you have also more cloudiness. And so you see on the 2 meters temperature of the clouds due to the trapping effect and long wave radiation effect. And also you see very well in the long wave down well. Actually, the anomalies in the north, as I was mentioning to you, the melting in the northwest and northeast is high because also these two areas, they were breaking records simulated, and they are consistent with measurements. They were breaking record temperatures in the northwest and northeast part of Greenland in the 1948-2019 record. And mostly because of the cloudiness. The clouds were trapping the radiation, they were promoting more heat. So in a nutshell, the story that started to take shape is that in the southern part of Greenland and along the coast in the east and the west, you have the anticyclonic conditions. The solar radiation is really playing a huge role because those conditions are promoting absorptions of energy. But at the same time, the same atmospheric patterns that are creating those conditions are also pushing all the clouds and the moisture in the northern part of Greenland, where they're sitting there and they're creating another effect that doesn't work on the short wave but on the long wave. And so it's really the combination of the two effects that is creating more and more of the melting and the extreme cases that we see. Yes?
So you're suggesting that the long wave effect is winning out over the short wave?
No, they're summing on each other. So on the southern part, the short wave is really the major driver, and the long wave effect on the northern part is really promoting more melting instead of the short wave.
Okay, so, but do you have a figure of the short wave anomaly?
Yes.
Oh.
Yes. This one.
Oh, yeah.
No, thanks. So again, I put it again, the cloudiness, that's the same figure as before. This is the short wave done well. And of course, this is what you expect. Yeah, more done well in short wave because you have less clouds, anticyclonic conditions, sunny skies for longer periods. But then, if you look at the combination of albedo and the short wave, this is really what you see, the short wave. So, on the case of the long wave, the long wave downwelling is really dry, driven by the cloud, and then you can see that matches the temperature in the north. But if you look at in the short wave, as I was mentioning to you, if you calculate the absorbed one, you really see that the overall effect on the side. So the two long wave and short wave, they play together to hit the ice sheet in two different ways, and they both basically were promoting melting. And if you look at again at the atmospheric drivers, this is the anomalies again in 2019 for the summer, June, July, August. On the left is 500 geopotential hectopascal. This is sea level pressure, and this is the 700. So this is one in the mid-troposphere. This is basically the surface, and this is between the two. The arrows also shows the wind directions for those for the same heights, and you really see that strong anticyclonic conditions up to 90 meters. Average anomalies in the case of the 500, but also you can see that reflected in some of the sea level pressure there, but also it doesn't really match exactly the 700. And so one thing that, and again, to go back also to what Clara was asking, you can see this is the time series of the Greenland blocking index. This is it's a proxy of the ML. The Greenland blocking index is calculated as the mean pressure, it's the mean geopotential height of 500 over Greenland, basically, over an area containing Greenland, and it's basically, it's the opposite of sign of the NL. So positive GBI means more melting in general, more anticyclonic conditions, where negative GBI less melting. And you see here that basically this is the summer GBI for average, and you can see that a lot of positive. There was actually the highest GBI anomaly value for the summer, but also what I think is interesting is that May, which is the precursor, of course, of the summer, it also showed the breaking record GBI value, followed by the lowest value in 2018. So there is really strong swinging between the atmospheric conditions that can promote this thing. And if you actually plot the runoff, for example, versus the 500 or versus the 700, because again we wanted to do this plot, you can really see that the 2019, which is this orange disk, in the case of the 500, it really falls on the 101 line, where in the case of the 700, which is closer to the surface temperature, is slightly biased, suggesting that atmospheric drivers were very much stronger, more correlated, of course, and more driving the runoff in respect to the surface temperature itself. So, of course, we wanted to look better at atmospheric conditions. So one thing that I've been, chasing and for the past years is self-organizing maps, neural networks. I've been doing this for a while, but we classified the 500 geopotential height from 1948 daily with our classifier. These are the classes. And again, all the figures are in the paper, so don't get too crazy trying to look at it, but this is the anomaly in terms of meters. And you can actually start looking at some of the classes that are occurring 2012 versus 2019. I mean, the beauty of this is that once you train the neural network, you can have basically the frequency analysis of your patterns. And you can say how many days one pattern was occurring, how many days were occurring, so you can create really good statistics. And in this case, we showed the red line is the, you have 28 classes. This is what you see on the x-axis. Now 28 because there was a guessing trial a lot of times, and that's how we decided to do it. But the blue is 2019, and the idea here is that how were the different atmospheric patterns different from 2012 to 2019. We're still not looking at the sequence, which I think is important. You still have to look at what if one pattern is followed by another, what are the consequences and what is the structure of the atmospheric during the summertime. But we can do this. In the meantime, if you look at the patterns that are more frequent in 2019, which are the ones here highlighted with the square box, and this dashed one was not really too high, but I wanted to keep it. They are mostly the ones that show super high, anticyclonic conditions over Greenland, and they are also different. The only pattern that is similar to 2012 is the number 20, which is this one. The rest, all the patterns that you see here that have a high frequency, so atmospheric conditions occurring in 2019, they are different from the ones that occur in 2012. And so I still, there's a lot of work to do, but what I did, I take these patterns, and then you can do again a frequency analysis. And you pile them up, and each color is a different class, and so you have a cumulative bar that shows you the total number of days over the 90 days of the summer where these patterns occurred. And you can actually see that in 2019, the combination of these patterns was really providing the highest frequency. So there was no other year before in which the combination of these patterns was as frequent as in this case. And this is actually what promoted a lot of the conditions, and the extreme nature of the atmospheric conditions intended as the first time that we see these kind of consequences to be able together and drive, of course, the pattern. So in a nutshell, you'll...
Sorry.
Yeah, go ahead, Clara.
Do you know physically, if you look at some of those, there's maps or there's classes, if they're more associated with cyclonic or anticyclonic wave breaking, there's kind of clear...
Yeah. So yes, that's a great... So the question is, do you know if there's any connection with the wave breaking on... So there was, for sure, the one in April and August. They were strongly connected to a very disrupted jet stream, basically. That's what we saw. I did not do it. In the past, I did the analysis of the waviness, and the ICAI is doing a lot of great work with the wave guides and that. And that's what I was thinking when I was looking at your talk. We should try to merge this, the two techniques and see what we can learn. But definitely there was a strong, the two events that are mostly, I would say 50% of the days when these conditions occurred are related to a strong, very wavy jet stream, very disrupted. So then I try to stay out of it because I'm not an atmospheric dynamicist, but I know there's a lot of work around it, but definitely it's something to look into that. And all these results are basically done, available. The frequency of this pattern is basically a matrix of 28 by whatever number of years for summer, so it's about something 3,000. So this is basically, in a nutshell, what I wanted to show you, because it's really important that 2012, 2019, they were so similar in terms of outcome, but they were so different. And what I love to do, usually I didn't show you here, it's a spaghetti plot for each summer. You can really see, if you assign a value of 1 to the classes that have the lowest, let's say GBI, geopotential high mean over Greenland, which you would expect to have less melting, and the higher values here, then if you do a cumulative time series, you can see that some of the classes that go up first, some of the summers that go up first, they will be basically more anticyclonic conditions sooner. So you can start seeing a lot of interesting patterns just looking at how the atmospheric patterns evolve based on the classification that we have. And this is something I did not do, but it could be done in conjunction with other analysis. And of course, with Clara, hopefully soon we will be starting to look at also extend GRIS into the stratosphere, but also look at the winter and fall with the NSF project that we got recently funded with the Judapo and Tormod, so that hopefully this will be will converge more toward understanding of the dynamics and so on. So I wanted to briefly highlight some of the work, and I think I have 4 or 5 papers. Yeah, people have to get to the bus to Lamont. Thanks for coming. First I wanted to mention the work that Paolo Colosio has done. Paolo is a master student from Italy. He's coming back the next 4 months. And we are actually working on, and we worked on developing an enhanced passive microwave resolution product. Maurizio Brodzik and Dave Young at Bingham University, they developed a 3.125 kilometers passive microwave product. And we actually used it, and we developed a 1979 to now time series of melt extent over both Greenland and Antarctica at about 3 kilometers. So this is the paper is in preparation, but the data is available in case people want to look at it. The second aspect is Shuzi's work. Shuzi, she's there, and you can wait. She's a postdoc at Lamont, and she had one of her tasks is to look at the presence of algae and bacteria over the ice sheet on the dark zone, and I had no idea how she was going to do it, and she had the brilliant idea of using ocean bands on Sentinel data to basically look at algae on the Greenland ice sheet, and so the paper was published recently on GRL, and she was able to demonstrate that not only you can do, but you can start looking at the concentration of algae and separation between the dust and biological material. And now, of course, Sentinel does not allow you to look at a long-term series because it's been launched recently, but of course, Shuzier, she was able, and she has a paper submitted now at the CRASPIR discussion, and you'll see here, and she's using Mary's data. Mary's is basically the brother of the sister of ModelE. It's a European one, but Mary's has more bands in the ocean color. You cannot do this with ModelE, basically. We tried everything, unless we didn't look at level 0 data, to be honest. We looked at level 1, level 2, but there's no information in the signal, basically. Yeah, it saturates, and also you don't have enough spectral resolution to capture the signal that you have, basically, from the chlorophyll. That's what she told to me in a year. But this is the time series of the evolution of algae over Greenland for the Mary's period, and it's the first time that this is distributed, produced. I don't know if this is, I probably got a wrong slide. This is the impurities, but there is also one for the algae, and you can look at the paper on the CRASPIR discussion. And all this information is moving toward the work of incorporating these processes into albedo, either in the regional climate model, but also in the ModelE at GISS. And Patrick Alexander, who was my student with me, postdoc, has been recently promoted to Associate Research Scientist at Lamont. So congratulations to Patrick. He is responsible for taking all this information and move all the stuff and code the stuff into the ModelE albedo. And he had, at the beginning, Patrick has been working with Elizabeth, where is she? Hiding under the sweater, with Elizabeth using elevation classes to improve the surface mass balance. So what Patrick found basically is that even though the ModelE was capturing the right surface mass balance compared to MAR, he was doing it for the wrong reasons. And so he has been working on, with Allegra, myself, to basically improve that. He published a paper on JGR recently on improving that. And he has implemented a new albedo scheme that he can account on not only for the snow processes, but also we're trying to use some ModelE's ancillary information to capture the bands. But then the next scheme, or the next idea also is, well, I'm going to skip this, but the next idea is also to basically to make everything physically based in the ModelE, so that you can start taking the snow grains, metamorphism, the impurities concentration, you take the model albedo into that, and then on top of that you add elevation classes. Elevation classes is basically a trick to resolve the process at a higher spatial resolution without resolving all the energy balance equations at a high resolution grid. So at the end you still have a grid size of the coarse resolution, but the quantities within are calculated by accounting for the spatial distribution within. So it improves things. And this is the preliminary results, and Patrick has been working on this. This is the difference between accounting with or without elevation classes. And if I'm not mistaken, Patrick is also basically adding the functionality to divide, as we agreed, to have albedo in different bands. Correct? So that, and the idea we had was like, why having an integrated albedo if we had to compare with remote sensor and other things? Let's make it as spectrally dense as possible so that we can extrapolate also information on different properties. And last but not least, the paper that we published, that Jesse, I never can pronounce this name. Nussbaumer. And Allegra, Patrick, and myself. Jesse is not here anymore. Where is he?
In car.
But the idea here was basically to use ModelE to see how moisture sources, and again remember the long wave and the clouds that we talked about in Greenland, how moisture sources have been changing in the past. And one of the major results, and the paper actually has been accepted, we got an email yesterday, it was finally accepted on GRL. And we found the only place where there was a statistically significant trend in terms of moisture distance from the place of the moisture sources was the northwest Greenland. So just divided the Greenland in 4 quadrants. You see here, this is the northwest quadrant, northeast, southwest, and southeast, and this is showing you the sources of moisture for the different quadrants. So basically what we found is that in the northwest Greenland, there is really this trend where the moisture sources have been getting closer and closer basically to the area we're observing. And it's still not, I don't think we can say if it's because there's been more production of moisture or because the sources have been pushing further north. I don't think we can say that, but
I think we decided it was ice removal locally.
Yeah, so there was, so there's all, but to our knowledge, this is the first time they were doing, and again, we were discussing about we want to do next steps to see if we can do some projections. And of course, when I look at this, the first thing that comes to my mind is clouds. You know, how do we improve and how much uncertainty we have on these because they're so hard to capture. So thanks to Patrick, Elizabeth, Shuzier, Raf is always there, is a visiting student from Utrecht. And he's working on varieties albedo in Greenland. Craig, believe it or not, he gravitates around also a group every now and then. We haven't seen you for a while, but it's always a pleasure to see you. Allegra, thank you so much. Thanks for everybody. I don't know if you have any questions, and thank you for being here. I needed to put a slide on the field. Yes, Jill.
Can you say a little bit more about the distribution of these factors like the algal blooms and contributing to changes in albedo over time?
Shida, do you want to say something about the time, how long?
Basically, the algae blooms, they bloom at the end of July and continue to the middle of August. And we also combine with ModelE's albedo, trying to see how algae blooms affect the albedo. So basically, like, the conclusion is that for each algae population doubling, the albedo will decrease by 2 to 4%. So this kind of is good. And basically, the algae for fast growing regions, like the doubling time is around 7 days to 10 days. We can double the population.
But it's also very tricky because as soon as you have a little bit of snowfall, then you mute the effect. Mm-hmm. So you have a doubling time as long as you have persistent supporting conditions. But if you freeze there or if you have a snowfall, then my understanding is that I don't know what happens to the colonies, but you might need to re-trigger reset to 0 your counting for the doubling time, because that effect is muted. And I don't know if it's because maybe it's spread away and it's covered. It's hard to say at this scale.
Because they are like tend to grow on bare ice, so that's why they are mostly occurred from the middle of July to middle of August, because that time period is the snow. There's no very few snow.
Cynthia?
Yeah, how important or what fraction of the lowering of the albedo on Greenland during the summer is attributed to algae as opposed to exposure to bare ice or just water?
Well, that's an open question, I think. Overall, I think in very small local areas it's very high. The question is, the more water you have, the more, of course, algae will be produced. So I think what you do is you really, as Sujay was saying, every doubling of colonies in terms of number, you have a reduction by 2-4% in albedo from bodies, broadband. Now, if you think that you go from a 6.7 of firm albedo broadband to 0.3 of ice, so that's a 50% relative reduction. So still the transition from snow firm to bare ice, and the fact that you have 0.3, 0.35 broadband bare ice, the 35% absorption, that is still the biggest change. And then to that you start adding, of course, the presence of water, which makes the surface of the ice darker, and then you have dust and algae. I think the relative contribution, I think overall we were not going to be able to quantify exactly how much is due to the algae, how much to the dust, how much to cryoconite and soot. Ultimately, we're going to develop a tool, call it a parameter, a darkening parameter that accounts for albedo changes as a function of the presence of melting. But I think that the algae can play a large role if you have a persistent melting, like in these cases. But I would say that probably, again, doubling time 3-4% on the doubling colonies. So I would say, to me, the greatest effect is really the exposure of the bare ice. And then to add is really the nuances of adding soot and algae. But if I had to say, would you be willing to spend more time and research on better including the algae in your model, or would you be willing to spend a better time on developing a better bare ice model? I would contradict myself. 4 years ago, I would say algae, and we got a proposal funded from NSF to do this, but now I would say bare ice and albedo, because that's something really that we have known how to treat physically. It can make a huge difference, because you can go from 0.4 to 0.3, so 10% difference just because of air bubble store, depending on which ice you're looking at. Thank you.
Just one.
Yeah, I'm here.
You said 2019 was hard because one of the reasons was the lack of snowfall in that surface mountains.
And that
Do you have any
because
idea why there's so little snowfall, given that you have plenty of clouds in the north?
well, no, the snowfall, it was the anticyclonic conditions really in the south that were not muting the albedo. So if you had, and this is why I think it's very important also to look at, and I'm hoping that people like, the atmospheric scientists or those who understand better than me this thing, you can have also the anticyclonic conditions sitting 50 kilometers more on the eastward side of Greenland. You will have a different situation. A lot of the anticyclonic conditions they moved from Europe this time toward the center of Greenland, rather than, as it happened in 2012, from the North American continent. They moved north, and they got stuck in Greenland, and they moved actually on the Arctic Ocean. In this case, they came from the other side, and they are related also to the strong heat wave that was in Europe. And so, where even just 100 kilometers different, or north or south, east or west, can make a huge difference, because that could drive more warm air or no, in 2018, there was a strong anticyclonic condition in Greenland. It was so much on the east side that all it was doing was actually sucking in, because of the cyclonic of the clockwise condition, the rotation. It was actually sucking all the moisture from the north of Greenland. And that, because it was cold and moist, it was dumping a lot of snow and increasing the mass. And that's why you see that 2018 is so low on the surface mass balance, because there were conditions, anticyclonic, but they were sitting on the other side, and all they were doing, instead of pushing all the rain there.
Sorry, there's another.
No, you can't be here, Redley. And that's it. So.
Sorry about that, I apologize.
No, don't, you don't have to. Redley has to. But thank you. I'm happy to keep chatting.